Let us solve the quadratic equation ax squared plus bx plus c equal to 0. So let's look at the notation. This is our quadratic where a, b and c occurring as coefficients are the elements of an algebraically closed field when we assume that a is not equal to 0. Because if a is equal to 0, this will not be a quadratic equation. Then our goal is to solve this equation by completing the square, and quadratic equations have typically two solutions. We normalize the equation now. You divide the entire equation with a, giving this equation, which is actually a monic quadratic polynomial. Monic meaning the coefficient of x squared is 1 into x squared. And then you move the constant term to the right hand side as shown. Now we complete the square. So you add this term b by 2a whole squared to both sides as shown, and you have the left hand side. We quickly recognize that it is the perfect square, x plus b by 2a whole squared, and we have added the same quantity to the right hand side also. Now we solve that equation by taking square root on both sides. So x plus b by 2a is a plus or minus. You have plus or minus on the right hand side, and x is equal to this quantity. There are two values here corresponding to plus and one corresponding to minus. Now the two roots are as shown here. This is the first root and this is the second root. So these are the two roots of the quadratic equation, and the b squared minus 4ac is normally called the discriminant. So when d is positive, you have distinct real roots. When d is 0, we have one coincident root, and when d is negative, we have two complex conjugate roots. Let's look at the summary. We complete the square, transforms the quadratic into a solvable square form. Then the quadratic formula emerges naturally from this approach. So every quadratic equation has exactly two roots. This method is foundational in algebra and connects beautifully to geometry and calculus.